Okay, in this lecture we're going to finish our section 3.3 material on trigonometric substitution. And we've been mentioning that this method of trig substitution can be used to integrate functions that involve a square root of a sum or difference of squares. Now more generally, we can use this method of trig substitution to integrate functions that involve the square root of a quadratic. Not necessarily just the square root of a sum or difference of squares, but the square root of any quadratic where a u substitution may not work. So as an example of this, let's consider the following question. Suppose that our integrand involves something of the form the square root of a arbitrary quadratic, ax squared plus bx plus c. Now we know for this arbitrary quadratic under the radical, we could complete the square for that quadratic in order to write it in terms of something involving a sum or difference of squares, and then we could use the appropriate trig substitution to evaluate that integral. So we can force integrals involving the square root of a quadratic function to be written as the square root of a sum or difference of squares, and then make a trig substitution to evaluate. So let's look at some examples of this. In our first example, we're asked to evaluate the integral of dx over the square root of x squared plus 4x plus 8. So the denominator here involves the square root of a quadratic, but we see that our quadratic is not the sum or difference of squares. So let us try to complete the square for that quadratic in the denominator. So here, I'll start by saying completing the square we have the quadratic under the radical in our denominator can be written as x squared plus 4x, and then in order to make this quadratic, x squared plus 4x, a perfect square, I would add 4. And in order to keep this quadratic equal to my x squared plus 4x plus 8, well, I have x squared plus 4x plus 4. In order to get a total constant value of plus 8, I need to add another 4. And this allows me to factor that expression in parentheses as x plus 2 quantity squared, and then I've got my plus 4 term on the end. So let's see what we have. Our integral of 1 over the square root of x squared plus 4x plus 8 dx is the same as the integral of 1 over the square root of x plus 2 quantity squared plus 4. So this now looks a little closer to a trigonometric integral or a trig substitution integral. We see that our denominator involves the square root of the sum of two terms squared. What's still a little bit tricky here is we don't just have x squared, but x plus 2 quantity squared under that radical. So this is a composite function, which might suggest that we try a substitution. So if we let u equal x plus 2, this inner function in our composition, then du is equal to dx. And so our integral, rewritten in terms of u, would be the integral of du over the square root of u squared plus 4. And now this looks like something where we can get or make use of a trig substitution. So let's choose u to be a, which in this case is 2, times tangent of theta, since we have the square root of a sum of two terms squared. So that would make du 2 secant squared theta d theta, and our denominator, the square root of u squared plus 4, reduces to 2 secant theta. So our integral du over the square root of u squared plus 4 can be rewritten in terms of theta as 2 secant squared theta d theta over 2 secant theta. So we can cancel a factor of 2, 1 factor of secant theta, and we're left with the integral of secant theta d theta, which is the natural log of absolute value secant theta plus tangent theta plus c. Since this is an indefinite integral, I can't forget my constant of integration. Now, going from something involving theta back to our variable u, well, let's take a look at how we could do it. We have the natural log of absolute value secant theta, and looking back at my earlier work when I made this trig substitution, I see I have this equation involving secant theta. If I divide this equation through by 2, then I find secant theta is equal to the square root of u squared plus 4 over 2 plus tangent of theta, and looking back at our equation where we made our trig substitution, if we divide this equation by 2, we find that tangent theta is equal to u over 2, and then we have our plus c. Or going back to an answer in terms of x, because remember we initially made a u substitution where u was equal to x plus 2. So if we want to go back to an answer in terms of x, well, let's substitute u back in. So we will have the natural log of absolute value square root u, which was x plus 2 squared plus 4 over 2 plus u. So actually I can have a common denominator of 2 here. So let's say plus u, which was equal to x plus 2 all over 2 plus c. So this would be my antiderivative of that function. All right. So let's look at another example involving completing the square. So for this last one, we're asked to evaluate the antiderivative of x over the square root of 3 minus 2x minus x squared. So our denominator involves the square root of a quadratic, but in its current form, that quadratic is not the sum or difference of squares. So that suggests that we might need to first complete the square for that quadratic so that we can make use of a substitution, a trig substitution. So here, let me start by saying completing the square for this quadratic, we have 3 minus 2x minus x squared could be written as 3 minus the quantity. Let me write it as follows. X squared plus 2x or 3 minus, for this expression in parentheses, I could complete the square by adding 1, and let's see what this buys us. So here, in order to keep my constants equal to each other, let's be a little careful. So in this step where I was completing the square, I added a 1 to this quadratic, but I was subtracting the entire quantity in parentheses. So I was actually subtracting 1 there, and in order to keep this quadratic as the same value, well, if I subtracted 1 from that quadratic, I also need to add 1. So let's see what we have here. Grouping our constant terms outside of the parentheses, we have a 3 plus 1, or 4, and then I was subtracting the quantity x squared plus 2x plus 1, but that can be factored as x plus 1 quantity squared. So looking at our integral, which was x over the square root of 3 minus 2x minus x squared dx, we can rewrite this as the integral of x over the square root of 4 minus the quantity x plus 1 squared. So now my denominator involves a square root of a difference of 2 terms squared. Again, as with our last example, the only tricky thing is that instead of just having 4 squared minus x squared, we've got 4 minus x plus 1 squared. It's a composite function, so I might start by making a substitution. So if I let u equal the inner function, x plus 1, then du is just equal to dx, and rewriting our integral in terms of u, well, we had x over the square root of 4 minus x plus 1 squared dx. In terms of u, our denominator is the square root of 4 minus u squared. Dx was just equal to du. And then our numerator is x. Now solving for x in terms of u, looking at our substitution, if I subtract 1 from both sides of this equation, I find that x is equal to u minus 1. So I'm left with the integral of this expression involving u, which to evaluate I could split into 2 parts. I have u over the square root of 4 minus u squared minus 1 over the square root of 4 minus u squared du. And I need to find an antiderivative for each of these parts. Now, the reason that I split it in this way is that this first integral can be evaluated by making a substitution, a direct substitution. However, this second term requires a trig substitution. We can't get away with a regular substitution there. So let's take a look at our first integral and see how we could evaluate it, making a regular substitution. So here I'm going to let u, well, I've already used u initially, so let me choose a new variable. Let me maybe say w equal 4 minus u squared. That is the inner function in my composite function for the denominator. So dw would then be equal to negative 2u du, or solving for du, I would have dw over negative 2u. Now, to handle this second integral, I can't get away with a regular substitution. I'm going to have to make use of a trig substitution, where u is taken as 2 sine of theta, so that du is equal to 2 cosine of theta d theta, and the denominator, the square root of 4 minus u squared, is then 2 cosine theta. So let's rewrite our integrals in terms of these new variables. So our first integral is given by the square root of u over the square root of what we called w, and then the du on the end, we said, is given by dw over negative 2u. So we see here that that factor of u will cancel on top and bottom, so this is why we can get away with a regular substitution instead of a trig substitution. And then we were subtracting the integral of du, which, using our trig substitution, is 2 cosine of theta d theta, over the square root of 4 minus u squared, which we said is 2 cosine of theta. So let's see what we're left with. We have, for our first integral, a factor of negative 1/2, which we can bring out in front. And then we have 1 over the square root of w dw, or w to the negative 1/2 power dw, minus the integral of 1 d theta. Our 2 cosine theta on top and bottom will cancel here. And so we are left with a negative 1/2 times the antiderivative of w to the negative 1/2 would be w to the positive 1/2, or root w, divided by 1/2, which gives us multiplication by 2, minus the antiderivative of 1 d theta would be 1 theta. And then, since this was an indefinite integral, I want my constant plus c. So let's simplify a little bit here. We've got a negative 1/2 times 2, which leaves us with negative 1 times the square root of w, which was 4 minus u squared, minus theta, and using our substitution, our trig substitution, well, we had u was equal to 2 sine of theta, so sine of theta is u over 2, and solving for theta, I would have arc sine of u over 2, with my plus c. And in the last step, to get back to an answer involving x, well, I'm going to take u, which was x plus 1, and substitute back into my answer here. So I have negative square root of 4 minus u, which was x plus 1, quantity squared, minus the sine inverse of u, which was x plus 1 all over 2, plus c.